So, yes. Okay. So now this is really neat. Some gory pictures here, but they actually work. And the bioengineering, which is a degree, kind of a new field pretty much, bioengineering, they're going to make those probes something that electrochemically interacts with a neurotransmitter. You know, these things that mechanical and biological are this interface. So, but it's all electrochemical reactions. So it's really interesting and important stuff. And I've got a bunch of examples on here. One complication, though, is that these, I don't know if it's convention or tradition or what, these guys don't like a lot of math. So what you do is you do a lot of math up front. Then the equation's nice and clean. You plug the pH in your body is close to what? 7. So then this nice little Nernst equation, which is really ugly, is a lot cleaner. And it's a lot cleaner by using E0 prime. But that gives us a job today. Okay, but we'll get there. It's not that bad. Okay, so let's start right off the bat with there's some probe, okay, and if you measure the potential, you can actually get the concentration of chloride, make this little, you know, calibration curve and things. But what's the math behind it? That's really what this is all about. Okay, so what the cell is about is, you recognize the left-hand side? That's that, we call it not the He, but the yeah, it's the anode, but the She, right? Okay, that's what that guy is. And then the other side, we have some chloride half reaction going on. But Pedro's exactly right. It's the anode. But I don't even like to memorize it, because I know I write down the half reactions. I just flip and do whatever I need to get the most positive E0. So why you don't need to memorize anode, cathode, all that. It's just, you just play with it, right? Okay, let's write down what those half reactions are. Man, you'd think I'd know what the She half reaction is, but I know you get 0, right? It's hydrogen. Involves hydrogen gas. A, B, C, D, F, G, H, I. Okay, there it is. Okay. Now it is the anode side, so I'm going to write it the right way. So I'm going to cheat a little bit using what Pedro said. Because if it's the anode side, is it producing or reacting with electrons?
Yeah. No,
It's producing, because those electrons get kicked out and go from left to right. Right? So I'm gonna flip this, because I know it's going to need to be flipped. So I have hydrogen gas. And you don't memorize this, you just look it up. Find the She. 2 hydrogen ions and 2 electrodes. And what's my E0? Well, it's 0. So you don't know whether you're supposed to flip that one or not. We probably should have done this one first. Then we would have known. Okay. The chloride. Let's see. Where's the silver chloride? Probably should be with the S's maybe. There it is. Silver chloride. Okay. So if I look it up, I should have wrote this one first. Then you'd see how to write the top one. Let me write this one, what I found. Silver chloride solid goes to, well, an electron. Silver solid and chloride. And the E0 is 0.222. Okay. It would have made a lot more sense to write this one first. Why? Because you know the electron, it has to be written this way because you have a positive E0. Right? I should have wrote that one first. Because if I write this one, the bottom one first, I know then how to write the She. Make sense? Because the electrons have to cancel out. So I should have wrote the one with the star first. It would have made more sense. But anyway. Okay. Oh, I can't add them up. Let's, I don't know. Multiply by a half. Right? Or you could multiply through the bottom one through by 2. I just want to be complicated. So, but here the electrons will cancel, right? That's all that really matters. So I'll end up with a half hydrogen gas and a silver chloride solid. And that's going to give a couple, oh no, one hydrogen ion, right? Whoops. Yeah, forgot about that. Yeah, but I'll still have the silver solid and the chloride. And I have a positive 0.222 volts. So I wrote the half reactions and the balanced net cell reaction. Oh, and the Nernst. It wants the Nernst. Okay. Well, I guess we can do that down here, right? The Nernst. E is going to equal, what should I write first? Jeff? Remember the Nernst? E0 cells first. So it's the point. You don't have to memorize it. You just kind of look at the top of the quiz or the exam. E is E0 cell minus 0.0592, right? Minus 0.0592 all over n. My n is going to be, in my case, my n is going to be, yeah. If I would have multiplied through by 2, my little n would have been 2. But it takes care of itself. I mean, you're going to have different expressions in the Nernst depending on your overall reaction. It works out to be the same thing. You almost have to prove it to yourself and do it. Products over reactants, right? What do I have on the top there, Kimberly? Products over reactants. The Nernst is for what? Which one? We have 3 reactions written. Good point. Which one is it for? It's the net, the overall. Right. Because look, here's the E0 cell. So we're talking about the bottom one. So products over reactants, what would you write? Anybody help her? It's going to be H plus in brackets, Cl minus, and oh, what do we do with gases? Yeah, we do. And it's P. They want to use P. Now, this is electrochemistry. Now, I'll use the jargon. I don't know if it's going to help you remember or not. They want the thermodynamic expression, the thermodynamic equilibrium constant, and all that sort of thing. So that means you don't have concentrations, you don't have brackets for gases. You use a P. And here's a real good one, if you remember this. What were the units you had to have for the pressure? Oh, wow, that's good. Bar. I had to look that up. Okay. So I'll have pressure of hydrogen, technically it's its partial pressure, but raised to what power? 1/2. Right? Yeah. Okay. So you see how you'll have a different expression if you have a different overall reaction, but you'll get the same numerical answers. All right. What we are supposed to do here is, given a measured cell voltage of 0.485 volts, find the concentration of chloride. So that means we should have a number in here for everything for the concentration of chloride. So what should we plug in then for our E, Adriana? Looks like what, maybe? 0.485. Yeah, that's what they're going to read on the voltmeter. We can change colors here. We'll have the 0.485. That's going to equal the 0.222 minus 0.0592 all over 1 log. Let's plug stuff in here. How about the hydrogen ion concentration, Natalie? What are you going to put in for that? They had to tell us somewhere. Oh, there it is. But we have to do a little math, right? Oh, let's figure it out. It's 10 to the negative 3.6. Let's just figure out what that is. We'll make our question look a little bit better. 3.6 negative 10 to that power. I don't. Okay, what is it? 2.5? times 10 to the negative 4. Thanks a lot. My little solar calculator doesn't work in the dark. Okay, now we need, we're looking for chloride, right? So leave them alone. And then for the P, oh, please be in bars. It is. Now, if it wasn't in bars, I have to give you the conversion factor, right? So don't worry about it, but needs, okay, has to be in bars. And that's, so it's going to be 1 raised to the half, well, big whoopee, right? Okay. Now, how do you solve for chloride here? Let's fix it up a little bit, maybe. We can take the 0.485, subtract the 0.222, right? Divide it by the 0.0592. We can clean it up a little bit. 0.485 minus the 0.222 divided by 0.0592, and that's negative. And I got about a negative 4.44, I don't know how far you want to keep going there, equals the log of 2.5 times 10 to the negative 4 chloride. Right? I guess over 1, but so Erica, does this look okay so far? How do you get, what would you do to solve for that chloride? Raise, there you go, raise both sides to the 10. And I'll get rid of that log. I just still don't know where my 10, there it is. I got about 3.6 times 10 to the negative 5, right? Equals, now the log's gone, so 2.5 times 10 to the negative 4, don't forget about him, chloride. So now we should be able to get chloride. Okay. Natalie, did you get an answer? Did you get 0.144?
Yes.
Oh, great. And what units?
We're looking for concentrations, so it would be M.
It's big M. All right. If we were solving for a pressure, it would have been in bars. Okay, so there's our concentration of chloride. Okay, measure some signal on the probe, get the concentration of chloride. Okay. However, this is not a biological system, I guess. Okay, I added this. This is why I had to kick some people out of my office. Sorry, Jeff and other folks. Trying to get, because I noticed that this is really kind of missing, and I think it's kind of confusing without it. So if it's not in your notes, don't worry about it. Just kind of just kind of follow along. These biological systems, they want E0 prime. So how do you get this? It's going to be the Nernst equation, except it's going to be E equals E0 prime minus 0.05, right? So an E0 prime just collects a lot of stuff, and it makes it a lot easier for these poor mathematically challenged biochemists to use, I guess. I don't know what the reason would be. Anyway, here it is. Commonly used, okay, NPH. This is how you do it. First, we're going to write the Nernst equation, just like always. And then what we're going to do is look for these little terms. If there's a conjugate acid or a conjugate base, or this is, I just copied this from our book. If these are there, we need to substitute in these expressions. And you recognize the F's? Formality. That's the whole reason why this is complicated. Because if they give the formal concentration of some amino acid or some monoprotic weak acid, we know that's not its concentration. You have to do a full systematic treatment of equilibrium, and this is what you end up with. So we're just copying the results that you could have derived yourself. In fact, this would have been a good exercise when we were talking about that stuff. We probably did derive this stuff. So if you see an HA term, you substitute in this expression. If you see an H2A term, substitute in that expression. So this is just a diprotic acid, monoprotic acid, or its conjugate base. Okay, so we'll need to have that table handy if we have an E0 prime problem. So we substitute it in, to our Nernst equation, and then we have some math. We have to rearrange the Nernst, and what we're going to do is get this E0 prime term. It's going to contain a bunch of stuff. It's going to contain the E0 number. It's going to contain any constants. Now you can see some constants up here. K1, K2. What's K1? What's K2? Those are the... I wish they would have had them in there. I don't know why they don't. Not KSP1 and KSP2, but KA1 and KA2. They should have little stinking A's on there, because that's what they are. That's KA1 and KA2 for a diprotic acid. If it's monoprotic, it's just, oh, there's their Ka. Okay. So we have to pull a lot of all these constants out and the hydrogen ion term. Anything left over, just leave it in the log. So there's going to be 2 log expressions in the end. Well, we'll see that. Okay, this is the game plan. It looks ugly, but it's not that bad. It really isn't. Okay, I thought this was kind of interesting, trying to Google a problem. Anyway, FAD, kind of like Fadi. Some of you guys know Fadi. E0, he has some psychomotor problems. I just talked to him. I should have gave him a hard time if I would have noticed this. Okay, anyway, write a complete Nernst equation for this half reaction. Okay, well, it's the same as we always did it. E equals E0. Oh, don't forget that. 0.038 volts minus 0.0592 all over 2. Because we're writing the Nernst equation for a half reaction. You can write Nernst equation for half reactions. You can write them for overall reactions. They're just writing for a half reaction. So n is just the number of electrons in that half reaction. Log products over reactants, right? So we'll have FADH2, right, divided by FAD, and hydrogen ion to the second. Okay. Now rearrange the Nernst and get this E0 prime thing. So we want to collect the E0 constants in the H plus terms. Okay, let's see if we can do that. Okay. Now, that FADH2 part, do you recognize him? What would he correspond to? The H2A. He's the diprotic form. So we need to substitute this mess in. What is that? Concentration of hydrogen ion squared. Concentration of hydrogen ion squared times F. And that's going to be the formality of that diprotic acid, divided by hydrogen ion squared. Too bad I can't copy paste this, right? And then H plus Ka1 and K1, K2. Thank you, sir. Okay, so that's that one. Times... Now we have to do these guys. Oh, it's supposed to say FAD. And hydrogen ion squared. The log of that big, ugly mess. Okay. But do you remember, this looks really ugly, but it's not as bad as it looks, because what's the log of A times B? How could you simplify that or change the expression? The log of A plus the log of B. I don't know if you remember that, but that's playing with logarithms. That's the log of A plus the log of B. So what we're going to do is we're going to collect all that stuff, all right, all the constants and H pluses. So can I see if I can circle all that? Whoa. And whoa. Right? Just pull all that out. Right? So you're going to pull all that out. You're going to end up with 0.038 volts minus 0.0592 times the log of everything I circled in orange there, plus the log of F over concentration FAD. Ah, what happened to green? There it is. Now I'm going to cheat. I'm going to do my orange trick. Where's colors I use on this one? Right? Okay. There it is. Okay. Minus. Right? Well, it's this guy. If you want to draw parentheses around him, all right. It's that 0.0592 times those two logs summed up together. So I need that 0.0592 over 2 again.
Isn't it plus the log since they're multiplied? Yeah, but
Log of A times the log of B is log of A plus the log of B. Okay. So this whole ugly mess here, I need to use red or something. There's our E0 prime. All of that is E0 prime. We can just keep it all like, who cares? I get your calculator. Why simplify it? Just plug it all in.
first half is their E prime?
E0 prime has to contain all the constants, all the H pluses, right? And the E0. So you leave everything else out. Okay. Then what is the value for E0? Well, I'm not going to do it, but we can't even because we would need to know what the Ka1 and Ka2s are. But we can get 10 to the negative 7 would be the hydrogen ion concentration, so you would plug it in. Okay. So it looks ugly, but it's, I guess it kind of is. All right. All the H pluses have to get pulled into.
So you leave that FAD out, and that's why it's in that formula at the bottom. Right, so.
I left the FAD in. Should I have substituted in for him too? FAD would be the A-2 guy, wouldn't he? Is there an A-2 one? Oh, there is. Ah, I picked a really ugly example. Nyla, you caught something there. Here's a candy bar, imaginary, right? So this is, we ain't need to substitute all this in there yet for that FAD. Because that's the, all right, that's the dibasic form, the A-2. All right? But that, don't worry about it. That's way too much. I think a much,
That's what we're supposed to do, right?
that's what we forgot. This is a real ugly, see, that's what you get when you do a real life problem. But this guy, we need to substitute it in for A-2. We need to substitute in all him yet, which is okay. We could do that. But let's go on to a monoproduct problem, which I probably should have had first. All right, let's try a monoproduct problem. Okay, but it gets a point across. We'll do the monoproduct problem. But do you see the idea? Right? You write the Nernst as you're supposed to write it, and then you look for those anything that's an acid or a base, conjugate acid or conjugate base, doesn't matter. The general way of saying it is HA or A minus, H2A or HA, or right, all those forms of conjugate acids and conjugate bases. Look for them and substitute in that from the book, all those expressions that they got from the full systematic treatment. Because when you say formality, that's the number that they're going to say, hey, this is a, how do you pronounce that thing? FADH2. This is a 3.8 formal lipoyl dehydrogenase solution. Right? If it's 3.8 formal, well, that's what you substitute for F. Okay? You just put in 3.8. See, that's why it's so much easier for them, right? If you'd use E0 prime. You go through all this work once, life is so much easier. For all the dudes that are there, okay? All right, let's try it. So I want you to work on this one. Okay? So write the Nernst equation. Okay? Write the Nernst equation first. And then you look for those little terms that you can substitute in for. Look for the conjugate acid or the conjugate base. But write the Nernst equation first. That's where it starts. And remember that if you forgot what the Nernst is just E is E0 cell minus 0.0592 over N log of Q, right? If you're not sure where to start, just to ask. Good. Use a P for the, because that's a gas, whatever. How would you pronounce that? Dicyanide gas or something? Dicyano gas?
You would have to square the PCN, right?
No, that's a little 2. It's like O2 gas. Would you square them?
Constant in front of it.
Yeah. If you had O2 gas, you don't square him, right? There's a big difference between a subscript and a superscript. There you go. Then that would be PO2. Oh, yeah, big difference. The hydrogen ion has to be in brackets, right? But and it needs to be squared. Right. Yeah, it ends in the number of electrons. If it was an overall cell reaction, it'd be the electrons that cancel. But we just have a half reaction, so it's just going to be 2. N is always the number of electrons involved in the reaction. So in this case, it's easy to see 2. Products over reactants.
Yeah, that's number in front, you square it, right?
We always do. That's how we write equilibrium constant expressions. Everything we did before is the same, right? Concentration of HCN squared, nothing new. Okay, so keep going, and look for the conjugate acid or the conjugate base forms. There's only one, and substitute in for them. You don't have the table. I need to, unless someone brought their book. Sorry. All right, the one that you're looking for is the very top one. That's the one you're looking for. Looking for the very top one.
Are we going to have to memorize this for the test?
No. Do you memorize equations for my exams? Have faith, Kat. Have faith. Yeah. Better square the whole thing.
So everything's going to have a square. Oh,
So it's concentration of hydrogen ion times the formality of the AHA divided by the hydrogen ion concentration plus the Ka number. That's what it says.
And then we know the concentration of H plus, correct? We have the pH.
Mm-hmm.
Yeah, the HCl.
Hey, John, can you read that to me? What is the HCN again? Oh, you didn't write it down? Dude.
You took it
Jeez. This thing. Did anybody write that down? Nyla, did you write it down? Folks, I was up there for like 20 minutes. Yes, Amanda?
Okay, so if we can find the concentration of H plus with pH, can we substitute that value for all of the H pluses, even the ones in the HA formula? Or is it only involved the H plus?
Is this H plus different than that H plus?
It's just it's different from the one over the next one.
If you have an algebraic equation, you see x anywhere, a whole bunch of places, isn't it the same x?
Okay.
Right? It is. All right, so let's see someone who's written this thing down so they can read it off to me. John, did you get it written down now? Nyla, what is the HCN term? Oh my gosh. HS, H plus times F.
And then over H plus K.
You guys are H plus K.
Is that considered a constant?
Right? So does everyone agree so far?
Sure.
Where did I lose you?
No, yeah.
Oh, no.
Casey, did I lose you? No? Okay, now we want to get, what do we want to pull out of this log? What do we want to leave behind? It's easier. What do you want to leave behind inside the log? You want to leave the F there? Is the P a constant? P is the pressure of that gas. Is that a constant? P is just like another X. P is the concentration of the gas. Right? So what do we want in E0 prime? Just remember what you want in E0 prime. You want H pluses and constants. The only constants you're going to have are the K's. Right? They're the only constants we have to mess with. Look at that whole table. All you have are those acidity constants. Okay. So what I want to leave behind is definitely this guy and this guy. Right? So that's going to look like maybe F squared all over that P thing, that P gas, right? Okay. So that's, I'm going to end up with an F squared over that. Don't forget the minus 0.0592 over 2 times its log, right? So on the very back here, I'm going to end up with, see if you can see that. And we don't have to do it this way, but if you can see it, all the more power to you. Over the pressure of that gas. Right? That's going to be our last term. Okay. In fact, if you wanted to, you could, if you're really not strong with logarithms, don't skip any steps. E is 0.15 minus 0.0592 all over 2. Don't skip any steps. Let's break that guy up. Let's have the F squared all over the P, all over the pressure, times, right? We're going to gather him, and then times everything else. Right? So it's going to be times the H plus squared. And then you have the H plus Ka. Don't forget what? To square them. Right? And that's, you could have had this big parentheses with one square. And we have one other guy. Yeah, that 1 over H plus squared. Okay. So if you're not so great with logarithms, you might want to do this first. Then it's really easy to see. We're going to log of the F squared over P term plus the log of that big term. Okay? So get rid of this guy. Oh, I'm gonna charge for this one. All right. So rearrange it. So E is going to be .15 minus 0.0592 all over 2 log H plus all over H plus Ka. Right. I could throw my hydrogen ion term down there. Right. Okay. So hang on. Okay. So now, where is your E0 prime in this mess? It's the first how many terms? Well, when you count terms, terms are things that you add or subtract. So I have a total of 3 terms. It's going to be the first 2 terms. It will be my E0 prime.
So it's going to be everything but the stuff including the formalities.
Yeah, so this guy really, he looks like this. He looks like E equals E0. Doesn't this look a lot better? Look at what these biochemists. You got to admit, this looks a heck of a lot better. Doesn't that look so much better? I can see why they do that. Okay. So all you do is you plug in the formality of this weak acid, plug in its formality, and the pressure. Here's your sensor, essentially. Right? Very easy to figure out what these things are. Okay. But E0 prime is going to be those first 2 terms.
So
And
that is the answer.
well, the answer is, what is E0 prime, isn't it? Or what? Evaluate it. So what you need to do is, what are you still missing to evaluate that? You'd have to look up the Ka. Yeah, you'd have to look up the Ka. No.
HCN?
The Ka of the HCN. You need it. Everything else you have. Okay. And you can look up the Ka of the HCN. Okay.
How do we get the gas?
We don't care. The question is, what is E0 prime?
Oh, okay.
The question is, what is E0 prime? Okay.
So we're having a review on Monday?
Monday is our big review.